And so that there are a number of different parameters that contribute. We haven't told you yet about, well, we haven't shown you visually, but certainly the frequency, we showed you through the data that one of the radar parameters is certainly a factor, the frequency, and the spatial resolution. The geometry would be the depression angle, range, and height, and the kind of land, the land cover, and the landform. Now, when you put this all together, the one view graph, and trust me, there are hundreds and hundreds of view graphs of the data that capture the physical idea of what we're measuring, but in greater detail and is sliced in different ways. This is affectionately known to us that see it a lot as the funnel graph. We see that there is a wide spread at VHF of the mean sigma 0. And that spread lessens as you go to higher frequencies. And this is for general rural sites, 36 of them. And you see color-coded, hopefully those of you are looking at a color presentation and not black and white PDFs, the range resolution, and for the same range resolution, horizontal and vertical polarization, they're pretty much the same at 150 meters and at 36 meter resolution of the pluses and the x's, it's still about the same. So it's pretty much independent of polarization, it seems here. Now that was just general rural sites. If you look at the terrain types, we can break that down into forest, urban, farmland, mountains, farmland again, must have that a second time, desert, marsh, or grassland with few discrete scatterers, and break it to end terrain slopes greater than 2 degrees, less than 2 degrees, moderately low 1 to 2 degrees, and very low less than a degree, and depression angles high, intermediate, and low. And the data is all broken down into these different clutter variables in the data collection. And here we see the numbers for sigma 0 F for these different regions. And we know, as we'd expect, that urban clutter has a much higher sigma 0 than low depression angle, desert, marshland, or grassland, 32 dB, 31 dB difference. So, and it shows within the high relief or low relief, that's terrain slopes greater than 2 degrees and terrain slopes less than 2 degrees. And then also broken down into depression angles, what the forest numbers are. So when you take that data and you fit it to the different distributions, you can come out with Weibull parameters that can be used to model that data. And all this is taken from Billingsley's work in reference to. And here are the Weibull distribution parameters. Now the next set of data that was taken was to look specifically at the ground clutter and its frequency spectrum. And it has a modified antenna. The rest of the system is quite similar in external view. And it's an L-band system. The clutter measurements equipment was modified to generate this L-band clutter measurements experiment equipment, where we have the frequency is at 1230 megahertz, 32 dB gain, an antenna with 6 degrees in azimuth, 3 degrees elevation, 8 kilowatts of peak power, the ability to collect data at all 4 polarizations, 500 Hertz PRF, 1 microsecond pulse, uncoded CW pulses with another bit added in to see down deeper into the clutter, and a sampling rate of 2 megahertz. And this was used to look at the wind-blown spectral clutter. And this was some data. There's many pieces of data, a whole chapter of data in his book on the data that was collected, but this is just a sample of North Dakota cropland wheat data. When you had, on June 12th, we noticed this characteristic of the data, that there's an AC contribution. That is, the wheat is blowing back and forth at 12 miles per hour in this case, and with a DC contribution that doesn't move at all. And then when we go to the 7th of June, where there's 30% more speed to the wind, it gets wider, and there's a stronger DC contribution. Here is 67 dB is the total dynamic range, and here 61 dB is the total dynamic range. And that can be easily broken down into two pieces of the distribution. A piece that's the AC part, and a piece that's the DC part, with R being the ratio of the DC power to the AC power, and DC spectral density, which is a delta function, the AC spectral power density, AC or V. And here's that AC spectral power density in meters per second. And it has this form. It's an exponential shape with a parameter beta. Let's go take a look at that. Well, in the next view graph after this. When we looked at data, when Barry, I should say, looked at data with low wind, you see light wind is in here, that's green, and then red is with breezy, and then blue is windy. We see it spreads, and this is forested region 7 kilometers away. And so then what Barry did was model the relative power in light, breezy, and windy conditions for the AC component. And the exponential decay model, when you look at all the different data, from X-band to L-band, it varies. There's a variety of wind conditions, light through heavy wind, and over a wide dynamic range greater than 50 dB. Previous Gaussian and power law models break down at wide dynamic ranges, he found out. And you can empirically model the parameter beta by the equation you see there, where it's a function of the velocity of the wind in statute miles per hour. Now, when that stupendous, huge amount of work was done at low grazing angles. When you go up to higher grazing angles, say from 3 to 70 degrees, this view graph captures quite readily how the quantity gamma, which is the cross-section per unit area divided by the sine of the grazing angle. And it's well documented that, as you can see reference 6, that sigma 0 is proportional to the sine of the grazing angle in this region. Where this is gamma, size the grazing angle, and sigma 0 is the backscatter coefficient. That for urban areas, for open woods, cultivated land, and desert, that this gives you good data that you can backtrack into the cross-section. And these curves are Skolnick's estimates from data that Fred Nathanson published in reference 6. At high depression angles, sigma 0 can be large near vertical. As one would expect, you look straight down. And this angle regime of reflected energy is due to the backscatter from small flat surfaces on the ground. The total backscatter is the sum of the contributions from all those different depression angles within the antenna's beam. And for vertical incidence, sigma measured is less than sigma 0, exactly at 90 degrees, because of the antenna gain. For an ideally smooth reflecting surface, sigma 0 is approximately equal to the antenna gain. And the approximation for smooth sea, it's better with smooth sea than more rough land. It's lower for land. And sigma 0 is generally greater than 1, greater than 1 and greater than the resolution cell size. Now there's one other property that has to be taken into account when we want to study the spread of spectra, and that is if the antenna is rotating, the spectral spread of ground clutter backscatter. It's the case where the antenna is mechanically rotating at a set revolution. And for that FAA airport surveillance radar with a wavelength of 10 centimeters that rotates at 12.7 RPM, 1.3 degree beam width, it's got 22 pulses will hit the target within the 3 dB beam width, and the time between pulses is about 0.8 milliseconds. The spread in the clutter is about 15 hertz. So you can look up in Barton or Skolnick's books for the formula, which I give you right here, how they're derived. And the spread of the clutter is just either of these two, the omega and beta, the antenna rotation rate, and the beam width are related to the number of pulses in the 3 dB beam width and the time between radar pulses. So you can take either of these two formula and they give you the same spread in clutter. And now we'll look at C clutter. C clutter is dependent on a large number of variables, quite a large number of variables. And here again we have a cursive dimensionality. The radar frequency, but we've got to add it in the wind and the weather sea state, the grazing angle and polarization, cross range resolution and range resolution as with ground clutter. But the wind speed and the weather, which is characterized by the sea state, are two different ones. And also, if you're on a ship, the mean value of the clutter will be moved. And the mean sea clutter backscatter is about 100 times less than the ground backscatter. And it has the same, it's an area, it's characterized by sigma 0 and cross-section per unit area as land clutter is. And I thought just to give you an idea of, here are some pictures, courtesy of NOAA, and this is from a ship, and from the ship you can see a picture of Sea State 1, where the wave height is 0 to 1/10 of a meter, 0 to 6 knots, and calm, slightly rippled. Sea State 3, which is down here, which goes from a wave height of 0.6 to 1.2 meters. That's the range of the wave height above the mean, 0.5 meter to 1.2 meters, and I think of it as 10 to 15 knots, 11 to 16 knots, and slight and moderate. And then we get up to the Sea State 5, where we see whitecaps. And typically, naval radars are rated to have to work in Sea State 5, which is very rough conditions where you can have wave heights from 2 to 4 feet and wind velocities from in the mid-20s up to 27 knots. And usually when sea states are high, that's a little too high for most radars aren't, just about all radars, when they're in sea state 6, unless it's drastic conditions, they try to get to sea state 5 where their radars will work. And here we see the sea clutter parameters. We've got the wave height, the wind speed, the length of time and distance, that's called the fetch, over which the wind has been blowing, the direction of the waves relative to the radar beam. You can read the rest of them. The swell of the waves, the contaminants that might affect surface tension, the garbage floating on the water way out at sea, as there is too much of, and the standard radar parameters we've gone over. And data has that cursive dimensionality since it depends on all of these parameters. And Fred Nathanson compiled a large amount of data, upwind, downwind, crosswind, adjusting from incidence of depression angle to grazing angle, looking at median values adjusted to mean values, and he took data over a large period of time and a large variety of grazing angles. And here are the values which he got for grazing angle of 1 degree, and when you put that data together with a lot of other data that has been collected by NRL, Merrill Skolnick came out with these generic curves of hand-drawn through all the data points of the cross-section per unit area as a function of grazing angle for different frequencies and different polarizations. Notice that the sea clutter is independent of polarization and grazing angles at angles greater than 45 degrees, and the backscatter from the sea is less using vertical than it's less using horizontal than vertical polarization, and for low grazing angles, horizontal polarization, sea scatter increases as the wavelength is increased. Now, relative to the amplitude distributions, the distributions for sea echoes are between Rayleigh and log normal. That means the log of the sea backscatter is normally distributed. And generally, the sea echo for horizontal transmit, horizontal receive polarization deviates from Rayleigh more than it does from vertical. And for cell dimensions less than 50 meters, sea waves are resolved and the echo's clearly non-Rayleigh. We'll get into sea spikes in a minute. The distribution depends on sea state, and the echoes usually become more Rayleigh for higher seas. And for small cells and small grazing angles, the sea clutter is approximately log normal for horizontal polarization. And then there are two other things to look at. One is the velocity of the waves relative to the radar ship. That's going to affect your mean Doppler and spread and the sea state, and then also at the phenomena of sea spikes. This view graph shows the cross-section per unit area as a function of the wind speed for various different frequencies and polarizations at low angles and at higher angles. And notice that polarization independent at the higher angles. Okay, and this is a function of the wind speed. So wind speed makes the cross-section go up, but actually go down at X band slightly. Read that pretty readily. And now look at a few statements about the effect of wind and waves. Sigma 0 increases with the increases in wind speed and wave height, except near vertical incidence. The centimeter wavelengths, sigma 0 is highly sensitive to wind speed, and sigma 0 is greatest looking into the wind and waves. Okay. Now looking at sea spikes, a very interesting phenomenon. Here is some data that was published by Lewis and Olin at NRL. A good deal of interest has been put on this, and we see spikes in the data that are long in length, that is a second or two long, then they drop down, long, and these low grazing angle, sharp sea clutter spikes, sea clutter peaks are known as sea spikes, and they can cause extreme false alarms, false detections in your radar, because they're long enough to get a number of hits on them. Where we see sea spikes most is at high wind speed and low at small angles. It's this area that we see it, and it's at low grazing angle. A very good article was written by Meryl Skolnick, and is an invited paper for the radar conference that was in Rome this past year. I think it was 2010 or 11, I'm not quite sure which, but it's available on the web. And he has some very interesting things and comments about sea spikes at the moment. Okay, now summarizing sea clutter. The mean backscatter from the sea is 100 times less than that of the ground. The amplitude and backscatter depends on sea state and a number of other factors. We've gone over that. The platform motion of the ship-based radar and the motion of the sea gives the sea clutter a mean Doppler velocity. It's not zero. The mean isn't. And sea spikes can cause a false target problem, and they occur at low grazing angles and moderate to high wind speeds.